Hello again. This is video lecture 16.2, and we're continuing our study of waves. And we're focusing still on sinusoidal, transverse, traveling wave. Remember all those terms that we introduced in the previous lecture. Transverse wave means that you have some medium on which the wave's going to travel, and the wave is a disturbance of that medium. And if it's a transverse wave, then the disturbance of the medium is in a direction, say up and down, that is perpendicular to the direction the wave itself is traveling, say to the right. That's a transverse traveling wave. And a sinusoidal transverse traveling wave is one in which the waveform is a sinusoidal curve, like a sine function. Remember how you make a sinusoidal traveling wave, say, on a stretched string, a taut string, a string under tension, assuming it's a very long string, and it would normally rest on the x-axis. You just take one end, however far away it is, and you move that end of the string up and down in the y direction with simple harmonic motion. And you control the amplitude of that up and down motion, and therefore control the amplitude of the wave that you make. And you control the frequency of that up and down motion. How many times per second do you move up and down? And that determines the frequency of the wave. Okay, so that's the kind of wave we're talking about. And as I mentioned at the beginning of the chapter 16, waves contain energy. And a traveling wave transports that energy, specifically mechanical energy, from one region of the medium to another. Think of a tidal wave in water. That's definitely showing you that energy is being transported. So what we're going to talk about first is chapter 16, section 3, in which we're going to talk about the energy and power of a wave traveling along a string. And remember, if we talk about a wave containing a certain amount of energy and transporting that energy from one part of the medium to another, the rate of energy transport is the power associated with the wave. So we're really going to talk about power transport in a traveling wave, by which we mean the average rate of mechanical energy transfer. What's the rate at which mechanical energy is being transferred along the wave? Now, I'm going to talk you through the gist of this argument. I'm never going to ask you to rederive any of this argument, but I do want you to follow along and have some sense of what I'm saying. But mainly we want to have some ownership of the result we're going to get for the average power of a traveling wave. But first, before I show you talk about this static image on this screen here and all the equations that are there, let me show you a Wiley Plus animation of a region of string that would normally rest on the x-axis, but we've created a sinusoidal traveling wave, and we're going to highlight a little region of that string and watch it move up and down. Okay, so that's what we're seeing here. We've got an x-axis with the x in centimeters, and a y-axis with the y in millimeters, different scales on the two axes so that we can see the vertical part of the wave better. And what we've also done is highlighted a little region of the x-axis right around x equals 2 centimeters, a little horizontal region along the x-axis, right centered on x equals 2 centimeters. And that's just a region of the string that would be resting there if there were no wave. But we have disturbed the string, the medium, by sending a sinusoidal traveling wave down the string in the plus x direction with speed v. And the wave then, of course, deforms the string into the sinusoidal shape. So that length of string that would have sat right on the x-axis, centered at x equals 2 centimeters, is now deformed into part of the sinusoidal shape. And it's that black curve that's along the waveform but centered on x equals 2 that I'm talking about. That's now the actual string that would have been just sitting flat along the x-axis at 2 centimeters. But now it's been deformed into the sinusoidal waveform. And here's part of the point, that deforming of the wave into the sinusoidal waveform is a kind of like a stretching, like a spring might do. So there has to be some elasticity to the string just to make the waveform shape. And that stretching, like a spring being stretched, gives rise to elastic potential energy, U. Although it's going to be a tiny amount of potential energy because it's a little tiny piece of string, so we're going to call it du, where the du means it's an infinitesimal amount of elastic potential energy. Now that same piece of string that has been stretched and deformed and therefore has elastic potential energy is also, at this snapshot in time where we're drawing this picture, it was moving transversely. I'm talking about the piece of string itself. In fact, the red arrow denotes the transverse velocity u of that piece of string at that time. Remember, we talked about transverse velocity of a transverse wave in the previous lectures. So that little piece of string has a transverse velocity u, so it also has some kinetic energy. But it's just a little tiny amount because it's just a little tiny piece of the string, so we'll call it dk, where the d in front of the k means it's an infinitesimal amount of kinetic energy. And as I run the animation and the waveform travels down the plus x axis, that little piece of string is going to be continually moving up and down and changing its shape. So the amount of kinetic energy it has is continually changing, and the amount of elastic potential energy it has is continually changing. Let's run the animation and just watch it. Note the piece of string is that black arc on the waveform. It's continually changing its amount of stretch, and it's continually changing its up and down velocity. The red arrow in the animation is that transverse velocity u at any given moment. The green arrow that you saw, by the way, is the transverse acceleration of the little segment of rope. Let's watch it again. It's going up and down and up, and then it would go back down again. Okay? Note where that little string element has the most deformation and where it has the least deformation, stretch. This is where it has the least when it's at a crest, deformation. Where does it have the most deformation? I'm just dragging the time slider back. When it passes through the x-axis. That's when it's got the most stretch. But that's also when it's traveling the fastest. It's got the biggest transverse velocity, u. Note at the bottom, the trough of the wave. That's when it has the least stretch, like at the crest. And of course, that's also where its transverse velocity is 0. So interestingly enough, at the place where it has the most kinetic energy, that would be right there, it also has the most potential energy. That's going to be an important point. Okay, so that's what I want to show you there. So let me go back now to my notes, and I'm going to talk us through these equations. I'm not going to ask you ever to repeat them, but I want you to have some sense of, okay, I can see where he's going with this. All right. So the picture on the right is a snapshot of the sinusoidal wave, and it shows a couple different regions of the wave. It shows a region of the string that's at the crest of the waveform. That's at point A. That's where it has no kinetic energy because it's momentarily at rest, and essentially no potential energy because the amount of stretch is minimal. But what about this segment of the string at this snapshot that they've labeled B? That's the segment that has the most stretch and is traveling the fastest. So that little segment has a large amount, so to speak, relatively speaking, of kinetic energy and a large amount of elastic potential energy. Now I'm going to assume that for both segments, if the string were at rest on the x-axis, each one of those rope segments would be that long, and we're going to call that length dx. And each segment has a little amount of mass, dm. Okay, so how much kinetic energy does the segment right here at point B have at that moment? That's going to be right here. I know the print is small, dk. It's 1/2 times the mass of that segment, dm, times its transverse velocity, u squared. So I've just written that right here. But remember, important property of a string when you're studying traveling waves is the linear mass density, or mass per unit length, mu, in units of kilograms per meter. That's a property of the string we will assume we know. Then how much mass dm does our little string element have? The mass per unit length, mu, times its rest length, dx. And what's the transverse velocity, u? Well, we learned how to calculate that in the previous video lecture. It's calculated by taking the partial derivative of the y displacement with respect to time. We talked about that in the previous video. So I have to take the partial derivative with respect to time of y max times sine of kx minus omega t. I'm assuming a phase angle here of 0. And when I do that partial derivative with respect to t, I take the derivative with respect to t and treat every other symbol as a constant. K and x and omega all treated as a constant. And when I do that partial derivative, I get this expression for the transverse velocity as a function of k and t. You get minus omega y max cosine of kx minus omega t. So then you plug in and get an expression for the amount of kinetic energy of that little string element b in my drawing, dk. It's 1/2, the mass is mu times dx, and then the u squared is omega squared, y max squared, cosine squared of kx minus omega t. Then you do something that physicists and engineers are comfortable with, mathematicians rarely are. I will just pretend I can divide both sides of that equation by a small amount of time, dt. So on the left I have dk over dt, and on the right I put the dt under the only other thing on the right-hand side that's infinitesimal, that's the dx. And I get this expression right here. 1/2 mu times dx over dt times omega squared, y max squared, cosine squared of blob. But dx over dt is the rate of change of x. It's the velocity of something, and it's an x velocity, and the thing that's moving in the x direction is the wave itself, and that velocity is v. V, not u, because it's in the x direction. So I get this formula right here for dk, the kinetic energy of that little piece of string that I've highlighted there and labeled b in the drawing. 1/2 mu, mass per unit length, v, speed of wave, omega, angular frequency, squared, y max, amplitude of wave, squared, cosine squared of kx minus omega t. And this same point B, where the kinetic energy is the biggest, and therefore dk is the biggest, and therefore dk dt is the biggest, the elastic potential energy is also the biggest, because that's where the stretch is most. I showed you that in the video, the animation. So I get the same result, here's the point, for the rate of change of the elastic potential energy of that small mass element of string. And that would be written du dt. But it's exactly the same as dk dt. 1/2 mu v omega squared y max squared cosine squared blah. So now, the total instantaneous power transported by the wave, P instantaneous, is the rate of change of the mechanical energy, d by dt of E mechanical. But that's d by dt of k plus u. And here is dk dt, and here is du dt. They're exactly the same. So add those two expressions together symbolically, and you get this expression for the instantaneous power associated with the wave. Mu, mass per unit length, v, speed of wave, omega, angular frequency, squared, y max, amplitude, squared, cosine squared of kx minus omega t. Note then the instantaneous power in the sinusoidal traveling wave depends on you telling me what x location are you at and what value is the time. And therefore, this P instantaneous is going to be changing, fluctuating, and probably quite rapidly with time and position as the wave travels. We're usually not interested in that rapid, fluctuating, instantaneous power. We'd rather just have, basically, an average value for the power. Okay? So what we're usually interested in, whoops, pardon me, I meant to have the highlighter. We are usually interested in the time average power transported by the wave. Just tell us how much power is being transported on average. How do we find that from our instantaneous power? So now I've got a formula for P average, and this is the quantity, P average, that we will be using. What we do is we take our expression for P instantaneous, that's exactly it, but we do what's called a time average. We average that quantity, cosine squared of kx minus omega t, we average it over a time interval delta t for a fixed x. We pick any x we wanted, doesn't matter. And we average over a time interval delta t, where the time interval is a repeat time interval. Let me show you what I mean in this plot. So what I did is I took cosine squared of kx minus omega t and plotted that on the y-axis, t on the x-axis. To make the graph, I did a couple of things. I just substituted x equals 0. I said you just pick an x, any x, you'll get the same answer no matter what. So I picked x equals 0. Why not? Makes it easier. In order for you to see the graph, I picked omega to be 1 radian per second. Since omega equals 2 pi over the period, that's equivalent to picking the period to be 2 pi seconds. And then I plotted, using the program called Mathematica, cosine squared of kx minus omega t, with x equal to 0 and omega equal to 1. And it's that blue curve that you see in the box. Notice it's cosine squared, so it oscillates between 0 and 1. Not negative 1 and 1, 0 and 1. And if the period of the cosine function is 2 pi, because that's how I chose it, it turns out the period of cosine squared is half that, pi. So I went out from a time of 0 to pi, and I've shaded in a green rectangle, a box that is pi on the time axis and all the way up to 1 on the y-axis. All right, so what I have to do when I do a time average, it turns out, is I do an integral. I integrate cosine squared of kx minus omega t dt from 0 to dt. In our case, the dt is pi. And then I divide by the size of the time interval, so 1 over delta t. Remember, I've substituted x equals 0. Now that integral is probably something you would not be quite ready to do, but we don't have to do it in a formal way. We can do it in a graphical way. That's why I made the graph. Because remember, an integral is an area under a curve. So the integral of that cosine squared from 0 to delta t is the area under this curve inside that green rectangle. But I contend that the area under the actual blue curve inside the green rectangle is exactly half the total area of that green rectangle. Just kind of look at it a bit. You've got a lot of symmetry going for you. So let's just find the area of that green rectangle and divide it by 2. Well, the area of a rectangle is easy. Width times height. The width of that rectangle is pi. The height is 1. So the area is pi. And half that is pi over 2. So that the area under the curve within the shaded region is pi over 2. Then I divide that result from the integral by delta t, and I'll have what's called the time averaged value for cosine squared. But delta t was pi, so pi over 2 divided by pi, 1/2. That turns out to be a very famous result, so I'm going to circle it, and I'm going to say, even if you're a little bit uneasy with all the mathematical steps I did, here's what I want you to know. If you find the time average of cosine squared over the repeat interval, you get 1/2. Same is true for sine squared. Doesn't matter whether it's cosine squared or sine squared. The average value of cosine squared or sine squared over one repeat interval is 1/2. You will hear physicists and engineers saying that all the time, or just using it all the time. Oh, that's just cosine squared, its average is 1/2. Oh, that's just sine squared, its average is 1/2. That's a nice, simple result. So when we put that in for the average value of the cosine squared, we get this result in the box, which is the thing I want us to be able to use. It is actually a rather famous result when you study waves. And waves happen a lot in nature. And it's the average power associated with a traveling wave. Technically, it's a sinusoidal traveling wave. And it is 1/2, get you down, 1/2 times the mass per unit length mu of the string, the speed of the wave v, the angular frequency of the wave squared, and the amplitude of the wave squared. And those are the things that determine the average power of a traveling wave. Mu, v, omega, and y max. And the omega and the y max deserve a little more attention because they're squared in the formula. And when you square them, you make them more important. And so what I've written here below in this summary is what the average power transported by a wave depends on. And I've listed first in caps the most important one. The average power transported by a wave depends on the square of the amplitude. See, the y max squared? You will hear physicists and engineers saying that all the time too. Oh, the power of the wave goes like the amplitude squared. So if you double the amplitude of a wave, you quadruple the rate at which it transports energy. And that's one of the key things you want to take away. Yes, power of a wave goes like amplitude squared. It also goes like the square of the angular frequency, like the speed of the wave, and like the mass per unit length, or depending on the mass per unit length of the medium. Okay, so that's a result that we will want to be able to use. Just that result in the box. And to just know what determines the average power of a sinusoidal traveling wave. Amplitude squared, angular frequency squared, speed of wave, and mass per unit length of the medium. So with that, let me show you a little exercise that I want you to do for class engagement on Blackboard. Okay, so this next bit will be class engagement exercise on Blackboard. And here's what it says. We send a sinusoidal wave along a string under tension, and the average transmitted power is P1. So think of the picture that you see down there. We've got a piece of string, uniform piece of string, which, if just held taut and not disturbed at all, would lie on the x-axis. But we're going to take one end and we're going to move it up and down with simple harmonic motion. Okay? And we can control the tension of that string because we can control how hard we pull on it. We can control the amount of up and down we move it, so we can control the amplitude. And we can control the frequency that we move it up and down at, so we can control the frequency, and therefore the angular frequency of the wave. So we start out by making such a sinusoidal wave. You can see it's traveling to the right at speed v. And we're doing it in such a way with an amplitude and a speed from a tension and an angular frequency that the average power is an amount P1. That's given. But now we're going to make some changes to what we do, and we want to know how the power changes. So in the first case, A, we're going to double the tension in the string, but we're going to maintain the same angular frequency and the same amplitude. So the question is, what is the new average transmitted power P2 in terms of P1? So the way you'll write that for A is you will just tell me P2 equals some number times P1, and I want to know what that number is. When what I've done is doubled the tension in the string, but I've maintained the same angular frequency and the same amplitude. That's experiment A. In experiment B, what we do is we double the amplitude of the wave. That's not hard. We just move our hand up and down twice as far. But we maintain the same tension and the same angular frequency. Now what's the average transmitted power? Let's call it P3 in terms of P1. So now when you answer B, you're going to have to figure out P3 as some number times P1. P1 was the original power from the original situation, with the original tension and the original amplitude and the original angular frequency. So P3 is some number times P1. What's P3? And lastly, that should be a C, of course, we are to do this experiment. Suppose that we replace the string with one having twice the linear mass density compared to the original string, but we maintain the same tension, angular frequency, and amplitude as in the original case. What then is the average transmitted power P4 in terms of P1? So in C, you have to figure out what the average power is, P4, as some number times P1. And what's that number? So you can enter those answers for class engagement on Blackboard. I have one more topic I want to talk about on this video. We're moving on. We're going to be omitting Chapter 16, Section 4, and we're going to go into Chapter 16, Section 5, one of the most important concepts when it comes to studying waves. Chapter 16, Section 5 is about a phenomenon known as interference of two waves. Interference, we call it. Interference is a quintessentially wave phenomenon. You cannot have interference with particles, which are localized things, right? Localized in space. But waves, remember, are extended disturbances throughout space. And you can have a phenomenon known as interference with waves, an extended disturbance in a medium, but never with a particle. So let's explain what interference is and show you what it looks like. We're going to set up an experiment, if you like, a thought experiment, with very controlled circumstances so that we can key in on the most important aspect of this phenomenon called interference and what causes it, and then what you observe when it happens. So here's the scenario. Remember, interference is when two or more waves are combined. So you know you're not working with just one wave, at least two. So we're going to have two waves. We're going to have two sinusoidal waves moving at the same time on the same stretched string. Don't worry about how you would get that to happen for now. Let's just take it as a fact. We have two sinusoidal waves moving on the same taut string at the same time, and both moving in the plus x direction. And let's make those waves very similar. In fact, exactly the same in every respect except one. And here's what I mean. The waves have the same amplitude, y max. They have the same angular wave number, k. Remember, k equals 2 pi over the wavelength. They have the same angular frequency, omega. Remember, omega is 2 pi over the period. And the only way they are different is that there's a phase difference, phi, between the waves. That means the waveforms, the two sinusoidal waveforms, don't have to be lined up. If I use my hands to represent the crest, that's how I would represent a crest of a sinusoidal wave. That's how I would represent the trough. If I use this hand to represent the crest of one sinusoidal wave, and this hand to represent the crest of another sinusoidal wave, the crests don't have to be lined up. They could be, but they don't have to be. Here are the two waveforms, the actual wave functions for the two sinusoidal waves. We're going to label them y1 and y2, both functions of x and t. For wave 1, the waveform y1 of x and t is y max sine of kx minus omega t. Standard form we're using for a sinusoidal wave in this chapter. The second wave, y2, is the same in every respect except it also has a phase angle phi. y2 of x and t is equal to y max sine of kx minus omega t plus phi. So let me now show you with a Wiley plus animation plots of those two wave functions. I'm going to plot them on separate graphs. But remember, they're both going to be existing on the same string at the same time. So let me go to Wiley plus, but now let me change to a different animation. Okay, now you're seeing three graphs, but for now, please, I want you to just focus on the top two. One graph is drawn with a red curve, and the other one is drawn with a blue curve. And they both represent our sinusoidal waves. The top graph, the red curve, is y1. You can see the axis is y1 in centimeters and x in meters. And you're seeing a snapshot, an actual picture of the wave at a given time. Time 0, in fact. And you can see that wave 1 is a plain old simple sine wave at time 0. Okay? All right. Now the second wave function is y2. That's the blue curve with y2 in centimeters and x in meters. And this is another snapshot at time 0. But this one has been drawn with a particular value for the phase difference phi that's not 0. It's, by default, the animation chose 1.047 radians. And the point is that shifts the sine curve for the blue function relative to the red one. If I change the phi slider down to 0, let me try to get to 0. It might not be easy. I might have to use the little down box there and just enter that I want 0. Okay, then the red curve and the blue curve are exactly lined up with 0 phase difference, and you could say they're lined up crest to crest and trough to trough. See how they're vertically lined up? But if I have a phase difference phi that's not 0, like 1 radian, then the blue curve has been shifted to the left by some amount relative to the red one. And those are the two distinct waves that we're putting on the same string at the same time. The question is, what will we actually see on the string? That's what we're calculating here. So now let me go back to my notes. And here, now let's go to the next step. The net wave observed on the string. Note the word, observed. That's what we will actually see on the string. You only see a wave on the string. What you see is the net or total wave on the string. What is that? It's the algebraic sum of the two individual waves. Algebraic sum, add. If you want to impress people at a party, you can tell them you have learned about what is called the principle of superposition. That principle says that what you would observe for the actual wave in the medium is just the sum of the two waves that you had. Algebraic sum with symbols. So I'm going to show you how to do the algebraic sum of those two functions, y1 and y2. Okay, here we go. Y net of x and t. That's the thing that you will actually observe on the string, that function y net. And that's obtained by adding the functions y1 and y2. So that's what I've done in the next line. Y net of x and t equals. Now I factored a y max out front because it's common. And then I have in square brackets sine of kx minus omega t from the first wave plus sine of kx minus omega t plus phi from the second wave. That's the algebraic sum. Now, if that's where we stopped, there wouldn't be much that we learned from that. You can't just look at that expression and have some light bulb go off thinking, oh, I can see what that's going to be. Not even close. But a little trig identity will make all the difference. So now let me remind you of a trig identity that I'm assuming at some point in your high school math you learned. I'm going to write it in a generic sense. It's the trig identity for the sum of two different sine functions. Sine of alpha plus sine of beta, where alpha and beta are two arbitrary arguments in the sine functions. You can, if you go through high school trig, you presumably saw a proof of this identity, right? It can be proved. We're just going to state the result. Sine alpha plus sine beta, it turns out, amazingly enough, can be written, notice I have a sum of two sines, as a product of a sine and a cosine. That doesn't happen with many functions. When I add two of those functions, I can write it as a product. But that's what you can do with the sine. And I'm just telling you the result. Sine alpha plus sine beta is 2 times the sine of alpha plus beta all over 2 times the cosine of alpha minus beta all over 2. And that's what we're going to use. We're going to apply that identity with, note, alpha being kx minus omega t, the argument of the first sine in our formula for y net. Oh, excuse me, the second one, because it's kx minus omega t plus phi. The second sine, doesn't matter which we pick, but then beta is the argument of the first sine, kx minus omega t. That's what I'm going to choose for the alpha and the beta. So let me just do a little bit of math here. Let me see what I get. Given those alpha and beta expressions, when I compute alpha plus beta all over 2. Just using those expressions for alpha and beta. So kx minus omega t plus phi from the alpha plus kx minus omega t from the beta, all divided by 2. This is just algebra. And what do I get from there? Well, I've got 2 kx's and 2 omega t's. So let's do 2 times kx minus omega t, and then plus a phi, all divided by 2. But algebra allows me to write that like this. Kx minus omega t plus phi over 2. Okay? That's alpha plus beta divided by 2. So, that expression is going to get substituted right inside that sign. So I'll show you that on the next slide in just a minute. But now, let me go back and do another calculation. Now, let me compute alpha minus beta, all divided by 2. It's a subtle but important change. That goes to a minus, and we better put parentheses around that blob so that we distribute the negative sign correctly. And we do not get the same result anymore. Let's erase the rest of that. Let's see what we do get. Well, now we've got a kx minus a kx. That cancels. And we have a negative omega t plus an omega t. That cancels. Wow, all that's left is phi over 2. That's it. So that's going to get put inside the cosine here. So let's see what the final functional form for y net is. And there it is. And it's important for us. The functional form for the net wave, the superposition of the two sinusoidal waves with the phase difference phi between them. This is going to tell us what kind of wave we're going to observe on the string. Okay, first I want to focus on this part right here. The sine of kx minus omega t plus phi over 2. When I see that, when I see the kx minus omega t inside the sine function, that tells me right away that I have another sinusoidal traveling wave. How do I know that? Because here's the thing. The hallmark of a traveling wave is that somewhere inside a function, you must have this combination of quantities, kx plus or minus omega t, where the k and the omega are just numbers, and the x and the t are variables. Doesn't matter if it's plus or minus, but that combination, kx plus or minus omega t, inside some function, then you know you have a traveling wave. Now, in this case, the function is a sine function, so I have a sinusoidal traveling wave. So what I've learned from that part I've highlighted is, by summing two sinusoidal traveling waves traveling in the same direction down a string, I get another sinusoidal traveling wave. Surprise, surprise. But I know this also, that it has the same angular wave number k and the same angular frequency omega as the original waves. Well, why not? Because they both had the same k and the same omega. So I get a sinusoidal traveling wave, traveling in the same direction with the same k and the same omega, but a different phase angle. Okay, fine. That's important to know. I get a sinusoidal traveling wave out. But here's really the key idea, and that's why I've got it in key idea and it's in bold. The rest of this result, which I'm now going to highlight, this part, the part multiplying the traveling wave part, everything out front of the traveling wave function is called the amplitude. Everything out front. So what I just highlighted in yellow is the amplitude of the resultant wave. Everything. Technically, amplitudes can't be negative, so we should put it in an absolute value. But other than that, that thing I just highlighted is the amplitude of the net wave. And here's the key thing. Just look at what I've highlighted in yellow. The amplitude of the resultant wave depends on the phase difference phi that I had between the two interfering waves. Here it is, I've written it down. The amplitude of the net wave is the absolute value of 2y max times the cosine of phi over 2. And it's the amplitude of the net wave that is really the thing we tend to look at when we have interference, because that's going to tell us the amplitude, how much up and down we're going to actually observe on this string. So now I want to go back to that Wiley Plus animation for the rest of this video and just look at the kinds of things you can see when you let these two sinusoidal waves interfere. So here we go. Back to Wiley Plus. And the first thing I'm going to do is set the phase difference to 0 between the two waves. Okay, so I'm going to set phi to 0. Then the two waves, the red curve and the blue curve, are in phase with each other. They're lined up crest to crest, trough to trough. If the phase difference is 0, then what do we get for our amplitude? Let's just use our new little formula there for the amplitude of the net wave. It's 2y max cosine of phi over 2, but phi is 0, radians. Remember, the cosine of 0 is 1, not 0, 1. So this gives me an amplitude of 2y max. Notice, that's the biggest amplitude I could possibly get when I combine these two waves. Absolute biggest. There's no way to get anything bigger than twice the original amplitudes, 2y max. So that's the absolute biggest I can get for the net wave. And we call that situation, when we get the absolute biggest amplitude of the net wave, fully constructive interference. Fully constructive interference is when you get the biggest possible amplitude in the net wave. Now I want you to look at the bottom graph on the animation, because that's a plot of y net in centimeters versus x in meters. Happens to be at time 0. And look at the amplitude first of y1 and y2. They're both 1 centimeter. And now look at the amplitude of y net. it's 2 times y max, the original y max. That was 1 centimeter. 2 times 1 is 2, 2 centimeters. That's the biggest amplitude you can get. That's what you're going to see, that bottom graph on the string. Okay, now when I run the animation, I'll just see the wave travel to the right. Right? I have a transverse traveling wave with an amplitude of 2y max traveling to the right. And that's the biggest amplitude I can get, fully constructive interference. Now let me point out something. It's not just phi equals 0 that will give me fully constructive interference. It's any value of phi such that phi over 2 makes the cosine vanish. And the cosine vanishes, excuse me, not vanish, but be a maximum, either +1 or -1, because we take absolute value. And that happens when the argument of the cosine is 0, or pi, or 2 pi, or 3 pi, or 4 pi, and so forth. So I'll get fully constructive interference when the value of phi over 2 is 0, which I just showed you, but I could also actually have plus or minus pi radians, or plus or minus 2 pi radians, or plus or minus 3 pi radians, dot, dot, dot. Because any of those values for phi over 2 would make the cosine be either +1 or -1, and that'll give me the amplitude of 2y max. Note if phi over 2 is any of those values, then phi, let's just multiply both sides by 2, would be 0, plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi, dot, dot, dot. So that's actually what's worth remembering. If the phase difference phi between the two original waves is 0 or 2 pi, positive or negative, or 4 pi, positive or negative, any even integer multiple of pi will get fully constructive interference. All right, now I want to put in a different value for the phase difference between the waves. Let's reset it to time 0. Let's put the biggest that I can get with this animation, slide the slider to the right. Notice it's 3.142. That sure looks like a good approximation to pi, and it is. Now look at the top two curves, y1, and now look at y2. y2 is shifted by pi radians relative to y1, and that gets them what we say exactly out of phase. Now the crest of wave 1, the red curve, is lined up with the trough of wave 2, the blue curve. Okay, so now what we've done is we've put in phi equal to pi. What's the amplitude of the net wave? Well, 2y max cosine of, note, for the amplitude, it's phi over 2. So phi is pi, so cosine pi over 2. But cosine pi over 2 is 0. So even though I had two waves oscillating, the amplitude of the net wave is nothing. Well, that's the minimum, right? That's the smallest possible amplitude I can get. Remember, amplitudes can't be negative of waves. That's the smallest possible amplitude I can get of the net wave, 0. So we call that, if the first case was called fully constructive interference, guess what this case is called? Fully destructive interference. And it's quite striking, because look at the net wave down there on the animation. It has no amplitude at all. And when I run the animation, my two original waves are traveling in the plus x direction, but I don't have, really, a net wave at all. Okay? Okay. Now, let's just note something else. When will I get fully destructive interference? Well, we saw when phi over 2 is pi, it would also work for, when phi over 2 is pi over 2, it would also work for negative pi over 2. It will also work when phi over 2 is plus or minus 3 pi over 2, plus or minus 5 pi over 2 dot dot dot. It goes on and on. Because for any of those values, you take the cosine of them, you get 0. Now, if phi over 2 equals that, let's multiply both sides by phi to see what the phi would be, the phase difference between the waves. It'd be plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, dot, dot, dot. So to get fully destructive, whoops, shoot, sorry, I didn't mean to do that. Phi equals plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, and so forth. To get fully destructive interference, I want an odd integer times pi. To get fully constructive interference, I want an even integer times pi, including 0. Now, you can have a phase difference that's not on this list. You can have a phase difference that's something other than an even integer times pi, or an odd integer times pi. Like you could have, for example, a phase difference of 1.75 pi. Right, then you'll get an amplitude for the net wave that's something between these two extremes, between 0 and 2y max. And you can see that all I got to do is change this phase shift slider to something kind of in the middle. So now the phase shift phi between the waves is 1.4 radians. And the resultant amplitude would be 2 times y max times the cosine of 1.4 over 2. Of course, that'd be the cosine of 0.7. So to figure out what that amplitude would be, you put your calculator in radian mode, you take the cosine of 0.7 radians, and then you multiply by 2, and you multiply by 1 centimeter, and you get about 1.53 centimeters. And if you look at the green curve at the bottom, the y net, you'll see the amplitude is about 1.53. So anything that isn't one of these is called intermediate interference. Okay, so that would be an example over here for this phi value. Intermediate interference. Okay, so the class on Friday is going to be all about interference. And we're going to do some applications of it so that you can get some more practice with interference of waves. That is the hallmark behavior of waves, that they exhibit this phenomenon called interference. All right, so we'll talk about that in class. That's all for this video.